Hello everyone, this is Exam Blueprint. Electrochemistry may look formula-heavy, but it's actually logic-driven. If you understand flow of electrons, everything becomes simple. In the next 10 minutes, we'll cover every board-relevant concept clearly and systematically. Keep your notebook ready. Let's go to Leah for the understanding.
Curtain on the secret life of electrochemistry. I mean, we use them every single day, right? But how often do we stop and think about what's actually going on inside that little power pack? It's this fascinating, high-speed dance of particles, and we're about to see exactly how the whole thing works.
At its very core, a battery is just a very, very carefully controlled chemical reaction. And what's the goal? To get a hold of the energy from these tiny particles called electrons and make them move in this perfectly choreographed, really powerful dance.
Okay, so to really understand that dance, we have to start with the most fundamental step. And that step is called a redox reaction. This is the absolute heart of how all this chemistry works. A redox reaction is really a two-part story. You've got oxidation, which is when a substance loses electrons, and you've got reduction, when a substance gains them. It's that simple. One thing gives, and the other one takes. And that little handoff, that transfer of electrons, is where all the power is hiding. And you know, a redox reaction can happen right in front of your eyes. If you just drop a strip of zinc into a copper sulfate solution, the zinc will just spontaneously give its electrons away to the copper. But here's the catch. All that energy just gets wasted as heat. It's powerful, for sure, but it's not useful. Yet. And this brings us to the big, brilliant question that basically unlocked modern electronics. What if we could physically separate the part that's losing electrons from the part that's gaining them? What if we could force those electrons to take the long way around? And the solution, it turns out, is beautifully simple. Just split the reaction in two. We can physically put the oxidation process and the reduction process in different containers. By doing that, we suddenly get to control where the electrons go. So let's see how this brilliant idea of separating things leads to the invention of something called a galvanic cell, a device that can finally capture all that energy from these spontaneous reactions. A galvanic cell, which you might also hear called a voltaic cell, is, well, it's a battery. That's what it is. Its whole job is to take that stored chemical energy and turn it into usable electrical energy by controlling that electron dance we talked about. This is the basic principle behind everything from a simple AA battery to the giant lithium-ion packs in electric cars.
Okay, so here's the whole setup. On one side, you've got the anode. That's where oxidation happens. The zinc is losing its electrons. On the other side, you've got the cathode, where reduction happens. The copper is gaining them. Now, because they're separated, the only way for the electrons to get from one side to the other is to travel through that external wire. And guess what? That flow of electrons is electricity. And that little thing in the middle, the salt bridge, absolutely crucial. It completes the circuit by letting ions flow back and forth so you don't get a charge buildup that would just stop the whole dance cold.
But hold on, that's only half the story. That's for reactions that happen all on their own. What if you want to make a reaction happen that doesn't want to? For that, we need to flip the whole thing on its head and look at electrolytic cells. This gives us a really great way to think about it. A galvanic cell is kind of like a waterfall. It's using a natural, spontaneous flow to generate power. An electrolytic cell, on the other hand, is like a pump. It's using power to force water uphill to make something happen that wouldn't on its own. So, an electrolytic cell does the exact opposite of a battery. You have to put electrical energy in to get the chemical change you want. A perfect example? Recharging a battery. You're using electricity from the wall to reverse the chemical reaction, basically pumping that energy right back into storage for later. So let's put them side by side. A galvanic cell, our battery, converts chemical energy into electrical energy through a reaction that happens spontaneously. An electrolytic cell does the reverse. Electrical to chemical, and it is not spontaneous. And check this out, the charges even flip. In a battery, the anode is negative because it's the source of electrons. But in an electrolytic cell, you have to hook it up to the positive terminal of a power source to literally pull the electrons away.
So, why does all this matter? What's the big deal? Well, let's take a look at how these two types of cells have completely, and I mean completely, transformed the world we live in.
Man, electrolysis is an absolute industrial powerhouse. It's how we create clean hydrogen fuel from just water, something that could be a huge part of a greener energy future. It's also the only practical way we have to produce pure aluminum.
In fact, the process uses so much energy that aluminum used to be more valuable than gold. And it doesn't stop there. We use it for everything from putting a shiny chrome finish on things to refining metals to incredible levels of purity. So you see, this isn't just theory from a textbook. The spontaneous reaction in a galvanic cell is what's powering your phone right now. And that forced reaction in an electrolytic cell, it's what helped create the lightweight aluminum in your car. Electrochemistry is, without a doubt, right at the heart of our modern world. It's pretty amazing when you take a step back and look at it. From this one simple idea, the transfer of a single electron, we've built this massive interconnected field of science that touches everything from how we store energy to the very materials we build things with. And that leaves us with one final big question. Our world demands more and more. We need better batteries, more efficient ways to create materials, new sources of clean energy. The fundamental principles of this electron dance aren't going to change, but the way we use them absolutely will. So the real question is, what's the next chapter in this incredible story going to look like?
Electrochemistry is logical, not difficult. Revise formulas. Practice numericals. Understand sign conventions. And don't forget to like this video and subscribe for more such content. Next chapter, we continue the sprint. This is exam blueprint. Structured prep, real results.